what I just showed in this example is that when you have when you have the dimension that is more than like 2, for example, 3x3 matrix, 4x4 matrix, you can do the most general way to get the determinant of the matrix. But if you only deal with 2x2 matrix, then things are easy. You just follow the formula here. Okay. And okay, so why determinant is useful? Because it tells us that if the matrix A is invertible, then if the determinant of the matrix A is not 0. Okay. Right. And a 0 determinant implies that the columns are linear dependent. Okay, so like this is like the two sides of a coin. Okay. Okay. And also the determinant can be used in the characteristic equations to find the eigenvalues here. Yeah, but I'm not going to talk about it here. Okay, so these are the properties of the determinant. So you can do the transpose first and then take the determinant operation and you still get the same thing here. And if you multiply numbers, scalars there, then depending on like how large is the dimension of the matrix A, you have to multiply. Like if we want to take out the C out of the operation, then we have to add the power of n on it. Okay, and for the determinant, the operation can be separate here. Okay, and the orders does not matters. Right. Okay, so this again tells you that for n by n matrix with the rank equals to n, which we will call it like full rank here. This matrix is also called non-singular. So there are a lot of like verbs or like terms here, and they are kind of related together. So if that matrix has the rank equals n, then we'll call it non-singular, which implies that the delta, not delta, like the determinant of A does not equals 0, and the inverse of it exists. Okay. Then is the eigenvalue and eigenvectors here. So I think like for the eigenvectors, there actually has some meaningful like geographic meanings there, but yeah, but I'm not good at it, so I'm going to show how to get the eigenvalue and eigenvector, and that's all. And when you goes to the when you take the course, for example, like macroeconomics in the graduate level, sometimes they will say that, okay, so we can analyze the whole systems and says that now we are kind of deviate from the steady point, and to some extent it's going to coming back to the original point. So that has something to do with the eigenvalue of that systems, but like you will realize how to use it when you see the problem. Okay, but I'm not going to cover. I'm not going to put that in the final exam. So don't worry. I just let you know, like this concept can be used in the economics as well. So that's the point. Okay. Right. So how to get the let's take a look at the definitions here. So for the so now we have a matrix A n by n here, and we also have non-zero vectors V. That V is an eigenvectors if it has a corresponding eigenvalue lambda, such that we can write it this way. Okay, so how to find the eigenvalue and eigenvectors? So follow the step here. So we already know by definitions, A times the vectors B will equals lambda times vectors B. So we move what is on our right hand side to the left, and because A is a matrix, so we need to put an identity matrix over there to make it so that you can do the matrix operations, right? So we can write it as this way: A minus lambda times identity matrix and times the vectors B. Okay, and of course, like this matrix is still n by n. Okay, and this matrix has a non-zeroed solution, which is V here, if and only if the determinant of it is 0. Okay, why is that? This equals 0 because all the columns are, the linear combinations of all the column vectors of this matrix A minus lambda in are linear dependent. Okay, and that leads to the determinant equals 0. Okay, that is the idea. So by using these conditions, then we can get the lambda, which is the eigenvalue and the corresponding eigenvectors B here. So here is how we are going to operate this concept by an example here. So once you get the matrix here, we want to know the eigenvalues and eigenvectors. So what do? You put the formula here. This equals to 0. Okay, this equals 0. Okay, and then what's next? Okay, because we want to note the vectors here, which is on the new space of the vector of the matrix A minus lambda times I here. So if we want to have multiple solutions here, then the only possibility is that the column space, the column vectors are linear dependent, and that's why we can calculate this using this equations to calculate it. And how to calculate these things? We can follow the formula above, which is here. Now we only have 2 by 2. We don't need to do the road operations. So that means it's equals to 4 minus times 3 minus lambda and minus 2. Okay, and this equals 0. And solving these equations will lead you to the following equals to lambda minus 5 and lambda minus 2. So the eigenvalue of this matrix is 5 and 2 here, as you can see from the blackboard or like on your lecture note. Okay, then this is the first step. To here, we already know the eigenvalues, and